Okay, hello everyone. My name is Judd Taylor, and welcome to, I think this is the third Atlanta Functional Programming meetup that we're having here in the common room on the second floor of a really cool building. Right, so this is a nice venue that we've got. We've got it now once a month until the end of the year, and hopefully it'll go longer. So again, my name is Judd Taylor, and Atlanta Functional Programming meetup was founded first primarily by Shay in the back there with the yellow shirt, and also by Ron. Very quickly conspired with Shay, and then I was fascinated by it and decided I'd volunteer to do kind of admin work and try to make events like this occur. So yay. How many of you found out about this through the Google Developer Group, GDG Atlanta? Okay, cool, excellent. All right. Yeah, thanks to them for putting the word up and then taking it back down, but I'm glad they put it up. All right, other things we have going on besides these are on Wednesdays, at least currently, Shay runs a small informal Haskell study group at the Dancing Goats, the one near here, not the one over near Ponce, okay, if you're interested in doing that. That's 5:30 till they close, which is 7 on Wednesdays, so tomorrow. And then also, we have Ram has been doing a series of virtual, Common Lisp virtual study groups. Virtual meaning it's online, right? We're not there in a room, we're there online. And they're recorded, and they're like an hour and a half to 2.5 hours long, and they're really good, and they're recorded. And so a lot of heavy, if you're into Common Lisp at all, they're great, right? If you're not into Common Lisp, you should watch them and learn why it's so great. Okay, then again, thanks to GDG, they've asked me to announce their DevFest, which is coming up. I think this is their third annual one. It's coming up on the 22nd of September, and of course it's the Google Developer Group DevFest, so it's focused on Google technologies. And there are tickets on sale right now, $35 for student and $50 for a regular one. And all the early bird ones, sorry, too late. Okay, now our speaker tonight is Lex Sheehan, who has a BS in computer science from Auburn, and has worked a lot at IBM, both in software and in services, and he's been designing and building enterprise-scale software. All right, he's got 8 patents. He has a blog that he sometimes writes on called Application Development with Lex Sheehan. He's written a book called Learning Functional Programming in Go, and recently he's had a lot of professional activity working with Ethereum. All right. Okay, so I'll hand it over to you. Is that cool?
All right. That's awesome. Thank you so much. Thanks. Can I just clip it here? Does that work? You're good. Okay, cool. Let's see, functional programming. Is everybody familiar with functional programming? How many people actually use functional programming in their jobs? Okay, awesome, awesome. All right. Well, this presentation it's actually all true, right? Using a fictional character called Tom, and he's got some friends, right? And so Tom's going to help us explore functional programming. But before we get going, I do want to say when I was reviewing this thing in the lift right over here, I found 2 errors in the presentation. All right. So y'all be on the lookout for that. If you're interested in a copy of my book, what happened, and we'll see this in the story, what happened. But anyway, a publisher found some article that I wrote about functional programming in Go. Said, hey, you want to write a book about it? And I said, sure. And we went through that, and we got right down to the end. They switched editors, and then what happened was they ended up publishing a draft copy of the book. Right, so I sent them an email and expressed my feelings, and some other customers had similar comments, and they were good enough to actually revise it. So it just got revised about a week ago, and they have the other number of copies, printed copies, in the mail to me. So if whoever finds the errors, and there are 2 of them, I'll have some contact information on the last slide. If you'd like a copy, I'd be more than happy, be elated to send you a copy. So be on the lookout for errors here. Nothing's perfect, right? Okay, so here we go. That's Tom, right? And Tom is excited about learning about functional programming. First, Tom was exposed to functional programming in JavaScript. And, oh yeah, this presentation, Tom is going to be in a number of poses. if you're a yoga enthusiast, you'll probably recognize some of these poses. But as we'll find out, learning functional programming is not about tightening your ass. It's about getting your head out of it. Okay, cool. Tom discovers lodash. Right? When Tom first saw it, he said, hey, this is a great little utility library. Let's see what we can do with this. We get an array of users, right, that have those, they just have one property, this example does. We'll start slow and move up a little bit. And then we have this cool little utility function called map. So if we pass this array of users into map and pull out the user keyword, we can get another array with just the users in it. Okay? And similarly, Tom found out that he could pass a function into the map and apply the function on each one of the elements. So if you pass this square function into the array of 4 and 8, you get 16 and 64. And so Tom was like, cool, I have no idea what higher order functions are yet, but this map function sure is handy. I think I'm going to keep using it. All right, so then Tom finds some other lodash goodies. This time, our users array has 3 properties in it. The name, the age, and whether it's active. He found a couple other functions. Filter, for example. We can filter by which users are active, and in this case, we get Alice. There's also the find function, and we use that to find, for example, using this Boolean expression, which ones are under 40, and Tom found Alice. All right, cool. Cool. jQuery. Does anybody still use jQuery? Anybody still use it? jQuery is awesome. There's a place to use, just about every technology. And I loved and I still do. Right. But here's the example you may be familiar with. Right. When you import, you import jQuery. But anyway, what's interesting, I haven't read, you have the same sort of filter in maps. So you can filter checkboxes on an HTML form, right? You just get the filter checkbox objects, and you pass those checked items into this map, and you're going to map and just simply pull out the names associated with each one. So cool. That's pretty much the same thing, but just with jQuery, right? And so Tom's like, hey, maybe I can write my own implementations, right? So Tom said, hey, I'll implement a map function. Right? In this case, Tom gets an array of emails. He happens to know the state of the application. In the state of the application earlier, Tom set what the new primary email address was. So he knows at this point in the program that will be set. So he's going to use that information to iterate over each one of these emails. So if it's not undefined, this way you won't get a null pointer exception. And then he can look at that and say, well, if that email is the new primary email address, then I'll set the primary attribute to true. Right? And so that's what that did. But then Tom thought, well, what could possibly be wrong about this stateful function? Is there anything wrong with it? So then Tom discovers functional programming in Ruby. Right? So Tom uses Ruby to perform some data transformation. I won't bore you with the details, but it's basically the same logic. And the overall picture of what's going on is you have 3 rows with about 8 columns, and he wants to pull out 4 of those columns. So the form of the data goes from the same number of rows, from 3 to 3, and just a different number of columns. Right? Easy peasy. Right? All this stuff's easy. It really is. So then Tom discovers this with index function that Ruby provides. Tom, by the way, loves Ruby. And with this index, right, it not just pulling off the item, but also the index, and then he's able to assign the index to this ID property, which is pretty cool. Right? So then Tom gets a little more fancy, and he discovers that you can actually chain functions. So as you're iterating, say like on each email or what was the other one, the users we had, we can apply multiple functions at the same time to each item as we're iterating on it. Right? So in this case, right? We get like some string, we split it, it becomes an array, we reject the nil items, so only items that are non-nil are we going to run some logic on and get some data, and it looks something like this, right? But then, now this new character shows up on the scene. See, says it's too complicated. That's corporate cliff. Right. Corporate cliff says we're replacing functional programming and this complicated language called Ruby. So can you guess what Tom does now? He can either follow corporate cliff or take a contracting job paying twice as much as he made working with Cliff. Right. So, but before we get on to that contracting job, let's trash talk Java. My favorite subject. Okay. Now, everybody, hopefully you guys, most people, does everybody know what this little guy is? The Go Gopher, right? So Tom uses his friend to illustrate that the general thinking among Go programmers is if you like design patterns, use Java, not Go. And so Tom's like, well, why? Why? You should always ask why. Why? You know, and what are design patterns? Well, so Tom, a number of years ago, wrote a site, it's on GitHub, Go Goodies, Go_oops, that's a real thing. And it outlines all the different design patterns. There are creational patterns, structural patterns, behavioral patterns. Right? And so Tom started implementing some of those. And as he started implementing these design patterns, he just felt dirty. It just felt like he was wrong. He just didn't feel like he was doing the right thing. So he stopped, and then he started listening to Paul. So here's what Paul has to say. He says, when I see patterns in my programs, I consider it a sign of trouble. The shape of a program should reflect only the problem that it needs to solve. Not a pattern. You shouldn't look at code and see a pattern. You should see a solution, right? And so, oh wait, I might have missed something here. Yeah, he talks about it sort of a sub-language, right? And what Tom was saying here is, you know, you don't need patterns, right? It's like it's sort of what's that term? It actually comes out of I think it comes out of the Gang of Four. It's an anti-pattern. See, patterns is an anti-pattern. Okay, cool. So, but that sounds reasonable. But you know, can you show me? Right? Show me why are you saying this? Well, Paul says you can replace the visitor pattern with generics. You can replace the factory pattern with closures. You can replace the iterator pattern with anonymous functions and the strategy pattern with high-order functions. Of course, that's sort of, well, generally speaking, right? There are exceptions to everything. Then Tom thought, well, doesn't the Go standard library have design patterns? Does everybody know what the Go standard library is? It's sort of like the Java JVM. It's like the system library, right? So it's like the code that the core developers of Go wrote that implements all the things like streaming and HTTP server and things like that. And it's great code, and you see the source code, and it's great to look to see for examples. And so Tom started looking, and he was like, hey, isn't this the iterator pattern? Right? That's clearly the iterator pattern. And if you interact with Postgres, right, you're going to notice the factory pattern, right? So maybe Paul wasn't 100% correct, right? So, you know, programming, that's why programming's kind of a dirty thing. If it was easy, everybody would do it. If it was simple and there was one way to do it, we'd just click a button and our code would be written for us. We have to use our minds. Yes?
So, you know, Paul Graham was talking about that in reference to like writing like a DSL, right?
Okay.
In Lisp, actually usually.
Oh, so you know this quote?
Yes.
Yeah. Okay.
So he's a big ardent fan of Lisp, and he writes
right.
his own Lisp. And his belief is for at least larger applications,
right.
is the architecture isn't set to based on a set of patterns, but instead of based on a set of sub-languages, subdomain languages that are particularly tailored to that domain.
Right, the DSL.
So
yeah.
I don't know. Can you actually mold Go that way? I don't think you could. could, right? Because there's no way for Go to allow you to do like meta programming in a sense.
Well, there's always a way. There's always, we'll talk after this, but and actually we don't go over. I'm not going over this in this presentation. There's only so much time. I mean, there's 163 slides as it is. but in the book, I go in depth about why Go does not support generics right now, and it's a whole big topic. So, but we'll talk afterwards. It's sort of a rabbit hole. Yeah. So we see Go's got iterator. It's got factory pattern. All right. So. Oh, yeah, let's get back on track. We're trashing Java, right? Okay, so let's talk about Java's infinite levels of inheritance and type hierarchies in JVM bloat. Right, so, okay. Has anybody here worked with Salesforce? Oh, I would not raise my hand for you. Yeah, I worked with it a little bit, and that's where I got this example from. It's just, can you look at that hierarchy? Think about how fragile that's got to be, right? And then let's just look at the big numbers, all right? We talked about the Go SDK and the Java JDK, right? The Java JDK is 280 megabytes. Go's is 13. The language specification for Java is almost 800 pages. The one for Go is about 90 pages. Concurrency implementation in Java is difficult. It's relatively simple in Go. Of course, I know you're shaking your head. It's like, if you know how to do something, it's simple, right? But we'll talk about this afterwards too, right? You can't fight these numbers here. I mean, the numbers are truth. Okay, and then you can look at this diagram, and it kind of shows why the JVM is so heavy with the just-in-time compiler and the JRE, the JDK. It basically is sort of like the target is the JVM. You can write in any language, right, and it does all this stuff magically for you. And actually, to get to some of the Haskell code that I wrote a number of years ago, I had to get the JVM. I had to get, because how it was set up, I was like, I just wanted to look just like I had it before. I had Java 8 running, and I needed Java 6. Okay, so if y'all want to go through the exercise of figuring out how to get Java 6 to work, it takes a while. I mean, there's complexity with that. Now, one thing that I want to say, I do want to say is, I think this is the last I'm going to. The last I bashed Java. Now I want to say Java 8 changes things. Java 8, I recommend it. What's that guy's name? Venkat wrote a book that was just super, super excellent about it. I wanted to include that in this presentation. I didn't have enough time, but Java 8 has got Lambda expressions. You can implement functional programming. It's definitely worth a look. Okay, so back to what Cliff said. There's lies, damn lies, and what Cliff said. All right, talking about the complexity, right? Functional programming is not complex, right? There's a lot of terms that sound confusing, but once you understand the terms and see what's really going on, it's not complicated. Now, Rob Pike, he's one of the founder developers of Go, and this is probably my favorite quote. Less is exponentially more. Right? Okay, so speaking of more, let's look at more functional programming in Ruby. All right, so Ruby has this thing called instance variables in a class. It's a mutable property that an object knows about itself. And let's look at an example. So here's an example of a payroll calculator. And I ripped this off of some site that I found just Googling. I have a reference at the back, but I just thought it was spot on, no need to change anything. It was just perfectly what I wanted to say. So here with Ruby, right there, that guy right there, the private class method is a little trick you can do in Ruby so that you make every instance that you create private. So basically what we did is we made this one function to calculate the only interface into this class. So it only has one public interface. And so what we can do with that is, like, we can, like if we want to call the taxes method, for example, right, it'll calculate and it'll look for, it'll first evaluate the instance variable taxes. Does it exist? If it doesn't, if it does not exist, what this pipe equal means is if it exists, use it. If it doesn't, then go to the right side, which means calculate the taxes. So the next time, for example, in pay stubs, you want the taxes, it'll go into taxes and it says, does taxes exist? It does, so it won't calculate it again. So, and that's called memoization. And another term for that is referential integrity. So in other words, we can replace a pure function call with its value. Very, very handy. Simple, super handy. Right, so we put some data in, assert that the result is what we expected. We only need to exercise one interface in our tests. So using pure functions can improve performance and make testing a breeze. So now let's go deeper in functional programming with Scala. Okay. What's a diplomatic way to replace a team of average Java programmers? Does anybody know? And this is like a true story. That's for real. Only one of the developers was able to hang with it. Okay. All right. So Scala, it's arguable, but I would say it's a big, complex programming language. It has imperative, object-oriented, concurrent, and functional programming paradigms. It's a gateway to large-scale frameworks, machine learning, data streaming like Spark and Kafka. People use Scala. Any Scala programmers here? Scala? Cool. Yeah, like it. And like with Scala, it's got so much, right? It's kind of like once you know how to do something, it's easy, right? Once you know how to do it, it's easy, right? But when you're first getting into it, it's like so big, right? So this was my first exposure to Scala. It looked something like this. It's a search entity price response. And I just pick out a few things in here. We got this little seek going on function here. I see map. Okay, yeah, that looks familiar. And there's a to map. So class extends. It looks like Java. Seek map to map. Well, that's something different. I'm not sure what it is. I'm very curious, right? So then I looked a little bit further in the code base, and I found this apply function here, and then we're defining what the entity element is, right? And it's getting a list and populating this little result, and it comes down here at the very end. It's like it's going to return either some value or none. And then after that, we've got filtered results that we can flatten, group by, map, merge, and then there's that seek again. So some, none, well, they're different than the high order functions that I'm familiar with. What else does Scala have in its functional programming little toolbox? It's got currying, tail recursion, high order functions, anonymous functions, lambda functions, partial functions, and everything is an expression. Right? So in Scala, mutation, the changing a variable, is the exception. You can do it, but it's the exception, not the rule. Okay, and that's one thing that makes things difficult when there are multiple ways to arrive at your result, right? Tom's just like, this is difficult, right? I see that we use recursion to produce results rather than iteration. That was a big one. That was a big head scratcher, right? Functions are first-class citizens, right? What does that mean? I'm like, what does that mean? And then finally, I realized, well, first, what is a first? Can anybody tell me or define a first-class citizen? Like, what in a language makes it first-class?
Yeah, it's a value that you can store in variables and pass to a function and return to a function.
It's like a data type. You can pass around like an int or a string, right? It's part of the language. Excellent, thank you. So Tom decides learning functional programming is key to understanding Scala and getting the most out of it. Okay, so here's the next chapter. So Tom, I'm skipping a bit because I've only got 163 pages here, but there was a part where he was doing Ruby and then went to go deploy Ruby and realized all the hurdles he would have to jump through to handle the traffic that he needed to handle with Ruby, the single-threaded language Ruby. So, so he founded a MQ solution called Beanstalk that allowed him to exercise all 4 cores at the same time, and he turned this program, this pricing matrix function that took 15 days into less than 24 hours, and he was thrilled. And then he discovered Go and realized he could write that himself, like in about a page of code, right? So he was like, oh my God, Go is what I want to learn. So he decided to write a website called Golang Code Examples. Right? And one of the articles is called Functional Programming. So he decided to share what he learns. Look, Ma, map and filter functions in Go. And then a new character comes along. He's called Publisher Paul. Nice article. How would you like to write a book? All right, so of course, Tom's happy. He's like, hey, research time. And this is what, in order to understand something like functional programming or any science, it's necessary to understand its history. So if you don't mind, we're going to jump into a little bit of history here. Okay, we're gonna go through it pretty quickly, but it's really easy stuff. So this is a journey into functional programming, according to Tom the Happy Cat. There are a lot of other guys that you could argue are more important, and I will skip one. But we'll start with George. Okay, George said Aristotle's algebraic logic was all in prose. It was all written. I translated it to symbols. So true to 1 and false is a 0 and so forth. All right. And then you got Augustus de Morgan, who said all logical operations can be expressed in terms of and, or, and not. Right? And there's the expressions here. And that's another thing. I'm going to take a step back and say, we're talking about the first-class citizens, right? And this algebra, right? When you can express a language and it's strongly typed, you can prove mathematically that your program works. And that's very, very powerful stuff. Okay, so then Frederick Fried created predicate logic. He studied the use of functions in logic and was the first to use currying. I mean, this guy was a badass, right? He said, if a tree is still on the power line, then we have no power. The tree is still on the power line, therefore we have no power. And here's an example of predicate logic. The book, like my book, is like 646 pages. It's got a ton of examples in it and tables of symbols and stuff like that. So the next guy was Lewis Carroll. I forget what his real name is, but that was his pen name. He wrote Alice in Wonderland, which seemed very illogical. You know, Alice in Wonderland and the falling down the rabbit hole. It just sounded just so crazy. But every part of the book was actually logical, like algebraically logical. And because of that, some of the functional programming references out there, like one of the big functional programming libraries is called Fantasyland, and it's referencing Lewis Carroll. So I found that interesting, so I put that in there. So these boneheads, Alfred Whitehead and Bertrand Russell, I'm sure they're super smart, but they're like, no, Fred, you're wrong. Okay, you're wrong, right? And they came up with this scenario called the barber's paradox. The gist of it basically is like, if you're a barber, right, and you're the only barber in town, you know, your hair's not going to be cut. You can't prove it. Your predicate logic falls apart, right? So they wrote a 450-page proof that basically showed that 1 + 1 = 2. Okay. Not very practical. So Moses Schofinkle, he's a Russian guy, he invented combinatory logic. And a combinator is a high-order function, like map or filter find, that only uses function application in earlier defined combinators to define a result from the arguments you pass to it. And it's a replacement technique that reduced multiple function arguments to a single argument, and that was later called currying We won't go into the details of the mechanics of how currying works. That's in the book, tons of examples. Then you got Haskell Curry. He formalized combinatory logic. He created the lambda calculus, where lambda expressions represent functional abstractions. And they're replaced by a limited set of combinators. And Tom's like, oh, is that where the lambda comes from? Of course it is. Well, I mean, not really. Lambda's like a Greek character, but anyway, this guy. Let's see. Did we? Oh, we hadn't gotten to him yet. My favorite guy here. Okay, I'm gonna skip Gerhard. All right, go to Alonzo Church. So Alonzo Church was pretty important. He came and said, I can improve upon Principia Mathematica. That's another thing. That's another thing. These guys, their book, right, where they proved that 1 + 1 = 2, the title of their book, they took it from Sir Isaac Newton's book. That was the name of the book that, explained all the laws of physics, right? And I mean, are you kidding me? I mean, that was sort of arrogant, right? But I thought it's pretty, real life history is humorous at times. So anyway, Alonzo Church said, I can improve upon that with effectively computable functions, right? Well, these other two guys, Klein and Rosser, quickly noticed that what Alonzo Church came up with was non-terminating, so the language itself could just keep running and there's no way for it to end. It sort of found a flaw in it. So he quickly responded with simply typed lambda calculus, which is a typed system with high-order functions upon which just about all functional programming languages are based. And so then Klein and Rosser were like, oh, that's cool, it's awesome. And then next up, which is really pretty it's really nice that this kind of worked out at about the same. So at about the same time, Alan Turing came up with the Turing machine, and he said, "Hey, my Turing machine can calculate anything your lambda calculus can, but I use loops and goto statements rather than recursion." Right. So, does anybody understand or not understand? But have you thought about the Turing machine and why most of the computers were based on that model as opposed to recursion, right? So these are basically the lambda calculus and the Turing machine, which is basic imperative programming. The Turing machine basically means I can compute anything. They can compute anything, just do it different ways. Why do you think most of the languages were based on the Turing model rather than calculus? Yes?
Because the Turing model can be finished, can end, and it's just less memory. It's more optimized because you have a 0 to 10. You can by the goto principle, you are sure that you're gonna end in the 10. In the other one, if you have a tendency of recursion, you don't know how much memory you're gonna allocate to run your program.
Well, that's not exactly, that's true, but not exactly what I was looking for. Exactly what I was looking for was the Turing machine is very machine efficient, right? Actually, what you said is very good. And I'm sorry I didn't have a slide for this, but when you're talking about recursion, what you say about recursion is absolutely true about a lot of languages, like Go, right now, and Java, and the JVM, right? When you, when a function, let's see if I have, actually I have to look down here. Where is it? Where is it? Okay, well, I don't want to ruin it for you. But anyway, a recursive program calls itself. We'll see an example here soon. Okay, a recursive program, where'd it go? A few more. Did it? I thought we did that one.
No, we did not do that.
Okay, we're right there. Okay, yeah. Okay, I'm sorry. I won't do that again, I promise. Okay, so, yeah, where was I? It was, the recursion, as opposed, and how that works. Yeah, okay, a recursive program basically calls itself, right? It's kind of like you're calling, Alice calls Bob, calls Cindy, and then they return back, right? It's just the way the recursion works. Okay, with the Java JVM and with Go and a lot of other languages, when a program calls itself the second time, it has to put all the whole program back on, what is it, the stack again?
Yes.
On the stack again, because there's a heap and there's a stack. But it's back on the stack, so the whole function pointer, the whole memory, it has to rebuild its context every time. Okay, but in languages like Haskell or Lisp, they have what's called tail call optimization. So every time a program calls itself, it's basically like a little go-to statement. It never leaves itself. Right? So that way it's very memory optimized. And if you read my book, I have I basically posted something to there's a place where you can say, hey, I think we should change our Go language a little bit. So I posted, hey, why don't we implement sort of a go-to statement? It ended up, like Rob Pike chimed in, 100, I think it's over 100 people chimed in from the Go developers group. It was like, it's so, to change a language, that's a great study in how, the implications of one statement, how that can affect a compiler. It was super, super interesting, but the net result is it's on the shelf right now. They're like, that's a great idea, but there are enough people saying that we got problems.
Is that the conversation about adding like a language, a feature from a different language that Rob Pike invented, where it started stumbling on that?
Well, yeah, it did. Did you? Yeah, but because and actually that's where they kind of came up with the term. I suggested go to, and then this other language they call it become. Because this function that we're in, right, becomes itself, right. So we basically never leave this program, right. And so there are so many people that were like, and I gave an example. Actually implemented the Y Combinator in Go, right. And so I use that as an example. I'm like, here's an example where we need this tail call optimization. And one of the first responses was like, well, I will use the Y Combinator exactly 0.1% of my programming career. Okay, so so you had all sorts of arguments back and forth, but it's interesting. And also, an interesting note in Java that I think Venkat pointed out is that even though Java does not have tail call implementation, you can circumvent that with clever Java code. And he showed a way to do that, which is pretty cool. Super, super smart guy. Okay, so next we got McLean and Eidelberg. They introduced the concepts of categories, functors, and natural transformations, and maps that preserve the mathematical structure as we saw earlier. John McCarthy created Lisp, the first programming language. And then we've got the Curry-Howard-Lambic correspondence. They discovered that there's a one-to-one, not a sort of like, but a direct one-to-one correspondence between objects in category theory, propositions in logic, and types in programming languages. So, if you start looking at that, the deeper you look at that, the more it'll blow your mind. It's sort of like, if there's an automobile accident. Right? You ask 10 witnesses what they saw, even though they all saw the same thing. Oh, crap. Hey, could I use somebody's computer? I think my battery just died. I've got, I did not bring the power adapter. I've got the PDF on this. Yeah, it's just a PDF. Yeah.
Is this the right power supply?
Yeah, I know that's a MagSafe B.
This
No,
is an
that's the
old
wrong
one.
version.
Yeah,
Okay,
it's an
sorry.
old one. Yeah, but thanks. Yeah, it's ancient. Yeah. Yeah. Yeah.
50. Man, that's cheap.
I buy mine used.
There you go. Here's a.
Okay.
Yeah. That's a good time for a break. Right. What's that? Yeah, I'll make them available online. Yeah. Yeah.
I'd love to get you.
Yeah, we haven't, yeah, the errors have not shown up yet. I'm pretty sure. Yeah, they haven't shown up yet.
So far, so if you count typos as errors. What am I doing here? I want to look in your, there.
Yeah, they're not typos. By the way, it's not typos. Yeah, they're actual logic, like, you know, what were you thinking sort of errors.
Is this a PDF?
Yeah, presentation. Yeah.
Just 1 second. Let's try and rehook your machine. Here we have, report this guy in, if you don't mind.
It's fine with me.
Thank you.
And I will get a power supply.
Hopefully. It will show up. Oh, okay. We're going to have to move this presentation to, oh, that's an extended. Is there any way to mirror?
I've never done it.
Oh, wow. Okay. Certainly.
Hey, I appreciate that y'all are still here. I mean, I really do. I mean, you know, it makes me feel good because at a point like this, you'd be like, I've been here long enough. I'm ready to bail out. The fact that y'all are still here, you know, I appreciate it. Hope you're getting something out of it. Yeah, yeah, yeah. If you hang in there, it's going to blow your mind. I swear it will. Yeah. Okay, while we're waiting on that, I'll give you a sales job for something else I'm doing. Okay, so in October, I'm going to be teaching a class called, well, anyway, it's cryptocurrency development, right? So if you're interested in blockchain development, right, the class is broken up between, I go into a history of currencies, right, to understand what cryptocurrency is. So I go into a history, much more in depth than this, but you know, to where you really get an understanding of what, you know, currency is, and then you understand what digital currency is, and we get into you know, developing a blockchain. We actually, and really, it wasn't until I actually developed the blockchain from scratch that I actually really got it and it clicked, right? So we develop a gossip protocol. You know, you can write it in whatever language you want. I have implementations in Ruby and Go. And so, you know, you implement public-private key. We actually use libraries, but you know, you use it in the program to create digital signatures, public-private key encryption. Like I say, gossip protocol. You know, you figure out how consensus works, and we sort of focus on Bitcoin at the beginning, and then you know, and then the second part of the class. We talk about creating smart contracts in Ethereum. So, you know, if you're interested in that kind of stuff and you find cryptocurrencies and blockchains to be kind of hard to grasp.
Over at the top, you get the file maybe.
Yeah, I'm just wondering if there's a way to put this into full screen again, but okay. Doesn't look like it. I think that's fine. We'll just work with what we have here. Try one more time. Yeah, it's not working. Oh, wait.
Hey!
You got it.
All right. That's good
too.
enough. Good enough. Okay. All right, y'all stop me if I go past it.
I just saw that error like 6 pages up. I get that right.
Okay, so we've seen that.
Just up here 6 minutes ago.
You saw your lives flash before you. Okay. All right, there we were. Yeah, mind blown, right? Right. Okay, category theory, logic theory, You know, lambda calculus and type theory, all related. And the book actually goes into how branches of mathematics, geometry, algebra, they're all related. They're just kind of like that car accident. You're all, the one thing happened, they're just different perspectives. Right? It's mind-blowing when you think about it. Okay, so then Tom thought, okay, this is cool, functional programming, but I remember working with flow-based programming you know, when Tom worked at IBM, right? And flow-based programming has basically 5 different tools. We've got read, write, split, transform, and merge. Right? And an example of using flow-based programming is a load balancer. Right? Here, what are we doing here? We've got a merge coming in and a split going out. Right? So the clients and the load balancer is going to load balance with the servers behind it. Okay. Oh, wait. Oh, yeah. So could this also be related to flow-based programming? You can discover the answer in my book, newly revised. All right. So what can we do with our flow-based components? We can compose, right? What does that mean? Let's look at some examples. That's the best way to learn, right, is with examples. Okay, so here we combine 2 smaller functions to create a new function that accomplishes the same goal as the 2 smaller ones, right? So you've got this F1 where you got an A coming in and a B going out, and F2 takes a B and returns a C, and you put them together. Right? You put A in, you get C out. That's like function composition. Right? All right, so now that was a little segue out of the history. We're back to the flow of the history of functional programming. Roger Gottman introduced the concept of monads, but it wasn't until Mogi, Wadler, and Jones that people started actually using it. So these 2 guys, Wadler and Jones, started using them in Haskell to chain functions, handle side effects, concurrent processing, logging, and more. But you see, it was Mogi that's like, we need to define a framework that helps us understand how data flows and you know, helps us put this theory to work. You know, so we need a framework for that, and that's actually, yeah, that's the monad structure. We'll look a little bit closer at it a little bit later. So, so even in 2006, Gibbons and Oliveira explored a functional programming solution to the iterator pattern, right? And so in other words, you know, we've seen this before. We've got 3 rows, 8 columns. We want 3 rows, 4 columns, right? And they showed how to do that, and the book goes into it. It's fascinating. There's actually a link in the book. I found that there's like a hangout that mathematicians go to. Right, and it's like this big thing, you know. It's like they put their little papers up there, and they have, you know, all the other mathematicians talking about it. It's really it's a good time to be a programmer. It's a great time to be a mathematician. It's actually exciting. So okay, so here's a little Venn diagram that Tom put together. Right, you can think about your favorite programming language and wonder, well, which circle is my language in? You see, the ones we've talked about so far are Go and Scala, JavaScript, Java, and Lisp and Haskell, right? Most of these are functional. A lot of these are multi-paradigm, right? They're both imperative, declarative, functional, and object-oriented. So I was going to talk about Java 8, but like I said, I didn't get to it. You know, I call it Go Plus. This is kind of like you know, you can implement a lot of things in Go, and Go makes it easy to implement stuff, so that's why I call it Go Plus. So, now, it's important to understand, I think it's important to understand category theory. So let's run through category theory as quickly as we can. What is a category? Right? It's simply a set of points and arrows that connect them. Okay? So we have, 3 sets of points. The A set, the B set, the C set, and you see the points, or we've got 4 points and the little arrows that connect them, right? So if we want to compose, remember we did that composition, we want to compose A, B, and C, and we got the A and C, right? We can follow the arrows and see, you know, how the arrows map from A to C, right? And there's mathematical expressions that we can use to represent that, right? All right, well, that's category theory. Let's look a few more details. All right, so let's look at what a function is. What is a function? What is a pure function? Right. So here we've got a pure function. Right. That's the function name f. There's the input value, and the whole thing is the output value. So if we have f of x, if f of x equals 2, and we input 3, we'll always get 6.
Error.
Error. Okay. Send me your email. All right. Okay. All right. So the first ones that send me the email, as many books as I get, I'll send them out. Okay. So good catch. All right. So function composition. Now we're going to take these two functions down here, right? F of x and g of x, right? So if we compose them or combine them, right? First, we're going to look at the g of x one and see we're going to use the coordinates, right? You remember from like middle school, x and y coordinates. So if we pass a 1 into g, you see we get a 3, right? So if we pass a 3 into this quadratic equation, a quadratic equation is just an equation that has an exponent, right? So we pass it in there, 3 squared plus 1 is 10. That's function composition. Okay, so let's look at sort of a code example of function composition. This is the typical way you see it, and this is why it's so confusing. Oh, by the way, this circle was just a way that I found it easier to draw the diagrams. It's really a point. It's not a big circle sphere thing. It's just a point. So when you go from A to B, that's the F. See, the arrow is a function. It's a morphism. We're changing something. We're going from A to B and from B to C, right? So an example I put in the book is, so for example, if we're right here, okay, so two people, one person owes somebody some money, right? So say Bob owes Alice some money, right? Alice can trust Bob to pay her this money every month for a year, or Alice cannot trust Bob and go through an attorney, and so Bob would pay attorney the money and then go from the attorney to Alice. Either way, money goes from Bob to Alice. You can either go directly or through an intermediary. Okay, so there's real life applications to this. Okay, so think about this. If you're an attorney and you're arguing a case, what is really going on? How does that work? And what does that have to do with category theory? Right? Isn't it the attorney that is able to map more of his arguments, right? More of his arguments to the case than the other attorney on the plaintiff or defendant, whichever one has more mappings and more strong mappings to the points in their case, that's the one that typically wins, right? So that's another example of category theory is all around us. Is a very, very useful mathematically based way to get things done. And here, this is what we're going to do. We're going to do the, and this is actually, I have this implemented in Haskell, I'm pretty sure. I might have done it in Go 2 in the book. But it's very simple. You start with a Boolean true, okay? How do you humanize true? With the English language, they say it's yes, okay? And then if you want to emphasize yes, give it a couple of exclamation points. So you start with a true, you humanize it, you emphasize it, you have yes, right? Now, all right, easy to understand, but does it work the other way? You know, can you emphasize first and then humanize? What does it mean to emphasize true? Can something be more true? No, it's true, or no, that's like a compiler. Yeah, no, it's a runtime error. No, you cannot be more. You're either true or you're not true. Yes.
Can you think of this kind of like matrix multiplication? Because matrices map between one domain to another.
Yeah.
And then depending on the basically those number of columns?
Yeah.
Different matrix spaces.
Yes.
Okay.
Yeah. So if you're doing matrix computations, functional programming is your friend. Yes, absolutely. Absolutely. Yeah. So let's look at, great question. Thank you for that. Look, function composition is associative. This little diagram shows how that works. It basically means you can either, you can either go from A to, you go, was it H of, see that's G of F, and then H, you can either go the red path or the green path. You can either compose, A and C, in C to D, or you can compose, you can go from A to B and then compose B to D. So in other words, function composition is associative. And so Tom's like, isn't that a math thing? How can we combine our functions for function compositions? How can we do that? Can we do some more? Give me some examples. Okay, now Tom wants to see if we can compose cows and tigers. In this case, let's add them. Okay, if we add this set and that set, right? See, we've got 3 cows and a tiger and a bad elephant. I went to Auburn, by the way. All right. We also multiply cows and tigers, right? So, isn't that cool? Now, what would exponents of cows with tigers and elephants look like? Isn't that cool? Right? But Tom wants more examples. Okay. In the presentation, I don't think, I can't remember if I put this in any of the examples, but basically, the category theory, right? You can get these, what we call them isomorphic equations, which is basically this side equals that side, okay? And they correspond, like, directly to the laws of exponents that we learned in middle school. I mean, it's like freaky crazy, right? And this is an example of what that Curry, whatever the lambic correspondence was about. And there's a guy. Let me show you this guy. This guy is super smart. This guy Wadler. If you look at his presentations, when he gives a presentation, he always ends it by ripping his shirt off, and he's got a big ass for
You mean the middle guy?
the lambda. Yeah. He's this guy. Yeah, he's lambda man, right? So he's hilarious. But anyway, he does a much better job explaining this. But actually, in the book, I think I do a pretty decent job. Yeah.
Tom does it pretty good.
Yeah, Tom. Thank you. Okay, so function composition. Now these are algebraic laws, right? Remember this from middle school: identity, commutative property, associative property, distributive property. Okay, so function composition is all good except for this commutative part, right? There's only a very special case where that's true. We basically just kind of discount it to say it doesn't really commute, right? So what does it have to do with logic? Let's look at a really cool example of this. Okay, A times B, that's the same thing as AND, right? So, and these are, see that's another little arrow, that's a function, F function, G function. All right, so both, when you do an AND, both F and G are required to produce the result, right? So, in other words, A and B must be true, for the result to be true. Okay. Now, conversely, right, if we're adding, right, it's sort of flipped around, and we still have our F and G, but in this case, either F or G are required to produce B, and if we're writing code, that's an if-then-else block, right? And here it is in the truth table. Right, it's super cool. All right, let's see.
Technical difficulties.
Seems to be locked up. Aha. Okay.
I'm sorry? We don't.
No, the air conditioning shuts off in like 15 minutes.
Okay, we're getting close. We're getting close. We're getting close. Okay. So Tom thinks to himself, what is the best way to clearly express functional programming so I don't miss any, so Tom doesn't miss anything? And he thinks, Haskell. Yeah, that's what Lambda Man uses, right? He's like the like the god of Lambda expressions and Lambda calculus. Let's use Haskell because Haskell's going to have the latest, greatest of everything. The thinking of the greats in this field will trickle down through Haskell. So let's take a quick look at that. All right, here's some Haskell code that implements this humanize, emphasize thing. I won't bore you with that. You can get the slides and look through it. Right, but it's very, the thing I guess is it's just so clean. Right, Haskell is just so clean. I wish that it compiled to multiple platforms. I wish it had a tight binary like Go. I wish a lot of things. I can't have everything, but it's a beautiful language. Okay, and Haskell has a REPL. It's like the Go interactive Ruby console, which is cool. Right, and so here we see the add to Lambda function. Right, the little backslash is the Lambda. A is the argument you're passing in, and here's the the array we're iterating over, and then your result will be where you add to there, which is cool. And this was super, super helpful. The Haskell type class hierarchy. Right, you can look in here and you can see, for example, here's the monad. So a monad is a monoid, right, and it's also an applicative. Okay, and the book goes into a lot of details about it, what all these different things are, but you can see there's a functor and a monoid, and it's even got an arrow, right? We'll talk about a few of the more important ones in a little bit. But what is a category? What's a category? We've seen this, right? It just sets points and arrows that connect it. What's a functor? Okay, a functor maps types to types. So, okay, let's illustrate a functor. Okay, if I got 1, 2, 3, 4, 5 over here, and the function that maps between is the multiply by 10 function, so it's 1, 10, 2, 20, and so forth. Right? So we can say our category is closed under multiplication and has the identity. What's the identity element for multiplication?
1.
1, good. And the identity for addition?
0.
Yes. You guys do know all this stuff. Okay. Well, thanks for humoring me. Okay. So how about an example functor? What about that maybe, right? Maybe sort of like a optional value, right? Now, with maybe, we don't have to worry about null pointer exceptions. What was that called? The billion-dollar mistake of Java compiler, null pointer exceptions? Maybe Go's got them too. Right? So, how is maybe defined? Well, there it is right there. It is basically, it's going to either return just the value, or if there's nothing there, it's just going to return nothing, but not the null pointer exception. What's a monoid? Okay, monoids allow us to combine values. Monoids are closed under the associative binary operation and has an identity element. Okay, we've seen all this stuff before. We can think of a monoid as a design pattern that allows us to quickly reduce or fold a collection of a single type in a parallel way. Where are the diagrams? Okay, I'll give you some diagrams. Okay, so we saw function composition before, right? We put in A to B, B to C, and we just compose that with A to C. But that's not a monoid. A monoid takes a type and returns the same type, right? So we have rules that we must follow for it to be a monoid, right? It's composition, but composition in a specific way, right? So here's an example of a monoid, right? Where we got A, it's going to A, that goes in and comes out, and A in, A out, okay? It's an endomorphism. En means same, morphism means function, endomorphism. Okay? We can combine them in any order. Remember the associative property? Right? So a monoid in any combination is still a monoid. And that means we can run them in parallel. Can you think of a benefit of being able to run a program, logic, in parallel? Scalability. Yeah. All right, so what's a monad? All right. A monad is just a monoid in the category of endofunctors. You know, we can actually understand what that means, right? So, but you know, duh, all right. But you know, Tom's like, yeah, that sounds great, but I've already forgotten what endofunctor means, right? Just show me some example. I learned by example. All right. First, you must answer a few questions, and I want y'all to think about these. You know, please don't yell out the answer. Are you a good person? Are you a bad person? Maybe you were a good person and you changed. What changed you? Where will you end up? Are you a kind of with Pascal and believe, you know, his argument or not? There's, you know, some people are like there's a heaven and a hell, right? What does that have to do with a monad? What does that have to do with programming? My God. All right. Well, I came with this thing called the Mother Teresa monad. All right. Here it is. Okay, so Mother Teresa was a baby, right? And she lived her life, right? And as she went through life, there were moments where she interacted with the world. So, for example, right here, maybe she was nurtured as a baby. She received positive input, right? Maybe later, with the dark arrow, she received negative input, right? Now, what do they say? Life is only 10% what happens to you and 90% how you respond, right? So maybe she responded, you know, with something positive. Maybe she helped other people even, you know, though she had very little. And maybe she continued like that. And I would, right now, I think she's in a pretty good place, right? But this right here, you know, this whole business right here, that structure is a monad, right? Right? And I didn't have time to put it in a slide, but in the book I have this, I draw a parallel between heaven and hell, and I make an argument that when you move out of the pure, right, this pure structure, and you move down into a place where, you know, you have input-output. Right, in this example, you have interactions with the outside world. I call that lowering. You're lowering your mind. You're getting down into the gutter of the earth, and you're interacting with it. Okay, it's called lifting. I'm just saying it should be called lowering. That's my argument. So anyway, Tom says, show me some examples. Okay, how about the marriage monad? Right. so best case scenario. Right. You come in here. Right. You get married. It's awesome. Right? What's an error? What errors can occur in a marriage? You can have a little divorce here, right? That's always a bad thing, pretty much. Yeah. So Tom's like, oh shit, I shouldn't ask that question. Right. Hey, that's okay. No worries. I'm glad you did. People have helped me through that journey. I used to think I was entitled, and then I studied the life of Charlie Munger. And I invite you to go look him up. So back to monads. Okay, explain that chain of boxes. Okay, so that you remember up here when we were talking about the where'd he go? This guy. Okay. See, this is all pure, and then that's like it's an error. We're going along great, we're married, we're happy, everything's great, and then we have an error, okay? So the error's down there. That's the way I depicted it. This just made sense, right? All right, so what we're going to have to do to make this make sense with a picture, and I think in visually. So what we're going to do, just bear with me, we're going to take this little errors, and we're going to move it around to the side. So we've got one input, and one output. No, actually 2 outputs now. We've got, you know, the data going along the flow, and then an error. Right. So what's going on with the 2 errors? The two arrows. Why 2 in and 2 out? So if you remember from the diagram, there's always 2 in and 2 out. But there's only one input here, right? How do you make that work? Where does the other one come from? Well, let's think about what we're going to do. We're going to create pluggable components like Legos, right? This path right here is the happy path. The red is like where an error occurs. Okay. Now, this is all about composition, composing our little Lego pieces, right? We can compose, we can decompose, and that's what we do. Isn't that what we do in programming? You know, we try to decompose the problem, we create little utility functions, and then we recombine them, right? And what's up with that purple? You remember that first arrow? If you were very observant, you would have noticed this purple, right? You know. So the little wise owl says, well, which one fits better, right? See where it's you know, this really doesn't work. It really doesn't fit. Right? It just kind of stops. Right? So how can we go from a 1-input thing to a 2-input thing? Well, that's the Monads bind operation. It's magic. It just creates it out of fiat, out of thin air, basically. So what happens if we get an error in the middle of our flow? Right? So if we have an error right here, does it just blow up? No, what happens is we start on the happy path, right? We have a little interaction, that's cool. And then down here we have another interaction. Maybe it's maybe we're logging data, and all of a sudden we run out of disk space. You know, we just got a hard crash, right? Something. Well, actually, you wouldn't want to have a hard crash. Yeah, okay, you can't continue processing. If you have, that's like a non-recoverable, not a good example. Okay, so you have another error occurs, and you know, you've got a failure, and you know none of the rest of the steps along the way make any sense. You go down the failure path. Now, okay, who can think of something that we probably use all the time that follows this exact pattern? No, I'm thinking about something specific. I sort of alluded to it with the REPL. Sort of like, yes?
JavaScript promises.
Well, maybe so, but I'm thinking about, I'm going to just tell you because you won't guess it. Who uses the Unix terminal? Who uses the Unix terminal? Okay, if you think about it, right, it's functional programming at its best, right? What is the data that flows? What's the common denominator of the data that flows from one function to the other? You know, is it integers? Is it some fancy objects?
Like entered in, entered out? It's just streams of bytes.
It's just a stream. You can think of it as a stream of text. It's a stream of bytes, but it's just a stream. So you just stream stuff in, you stream stuff out, and you've got what? Standard out, standard error. Okay, see this? Standard out, standard error. I wonder if those guys that came up with Unix and created the shell were functional programmers. I don't know, but it's the same pattern. So, does Go have monads? Well, it's not out of the box, but you can write your own. Or you can copy what I call the lexical workflow solution code from my book. I actually created a monad in Go, and I'm not sure. I mean, it was like original. I didn't, you know, nobody else had come up with that. I mean, I didn't copy it. Maybe somebody did somewhere, but I didn't see anybody's code that did it. In my mind, it was original, so I gave it a name.
So, did you need any dependencies to implement that?
No, it's all pure Go. All pure Go. Okay, so let's write some more Go, okay, or some Go. And why doesn't everybody use functional programming in Go? Okay, here's an imperative Go with the iterator loop, a for loop. Here's the recursive function that I was looking for earlier, a function that calls itself, right? So let's, in the book, I send it some data, right? I send it some data, and we see that the imperative is so much faster than the recursive. Yes, that was the second error. Yeah, so basically the imperative, these numbers should be switched. The imperative, you know, an example I gave is like 3 times faster, and it's because Go doesn't implement you know, the go-to statement, or tail call optimization, rather. Okay. So what options do we have? Well, you can use that monadic workflow, right? Or you can check out Gleam, which is an excellent library that the guys at Uber have been working on. And so here's some references to some stuff that I just pulled out just for this presentation. Some more references. There's a little book. It's newly revised. First people to send me the, you know, the two errors, you know, with the little other information, I'll be more than happy to send you a book. Okay, I covered the cryptocurrency class. You learn these things. And there's the last slide. So, thank you. Any questions? Any questions? Yes?
So, actually, I guess my first question is sort of off topic, and that is, are you talking about the blockchain conference coming up in Atlanta?
No. What I did here, the cryptocurrency developers class. Well, if you read the frequently asked questions, you can see exactly what it is. I basically, I've been working in cryptocurrencies since the beginning of the year, but it was sort of like functional programming when I first got into it. It's like it's such a big area. It's so confused. There's no really good examples. How do I get this going? And then I went to a class in San Francisco for an entire month. I did nothing but learn from probably the smartest dude. He was his name? Well, no. This is he's a guy that when he would, every time he would enter a poker, you know, the World Poker Contest in Las Vegas, he would win it. I mean, he's just a brainiac dude. Hasib, that's his name, Hasib. Anyway, so anyway, I learned from him, and then I was like, you know, I think I like teaching and kind of drawing diagrams and giving, you know, very visual explanations for things. So I said, well, they don't offer anything like this in Atlanta, or even on the East Coast. So I was like, yeah, I think I could teach this class. So, you know, so that's what it's about.
So are you teaching online, or are you teaching in?
No, it's in person. It's in person. It's in person. I may actually make, you know, online version of it at some point, but it's sort of a seminar style where, you know, if you have a problem, you come up and ask me. You know, it's actually like the course I went to in San Francisco. If you could take that, it's at a place called Bradfield. If you could take that, you should take it. I mean, it's just fantastic. You know, it's a small class, and you know, you make contacts there, right? You know, you're able to learn from each other. You get coding. You know, the coding examples you get are like sort of like, you know, like a little design document. You know, and it's sort of, you get as much as you put into it, right? If you want to just come and, you know, listen to the brain candy, you know, that's cool, but you're not going to get near as much out of it if you don't actually do the homework, right? Because the homework's going to have, you know, you're going to actually implement the gossip protocol, right? You're going to implement eventually the blockchain. You write your own block. You create your own cryptocurrency, right? And then, you know, you study Ethereum, Solidity, you know, all that. And I'm thinking, which wasn't in the class, isn't in the class in California, I'm thinking about you know, showing you how you connect them, right? So how do you actually, you know, add stuff to the blockchain? How do you know the blockchain changes? If you're running a side chain over here, right? So a lot of these blockchains, it may take you know, 10 minutes, you know, maybe 15 seconds, some longer period of time, but you want super fast transactions. So you're going to create a side chain over here, and you basically batch, you know, stuff. How do you know when something changed in the blockchain, right? How do you connect those two? Because a lot of times you look at these components and you're like, where? You know, how do you plumb them? How do you connect them? Where are the edges, right? So I may put that in the class. I hadn't decided, but anyway, you learn how to build a blockchain. And then, you know, about, you know, smart contracts with, you know, and it's Ethereum, so just about, you know, you learn about ERC20 tokens and stuff like that. So, yeah. Is that it?
So I just have a general question regarding actually on the talk, which is,
yeah.
So what, at what point did you decide, okay, you know, there are these little bits and pieces, primitives in Go that gives me some sort of ability to actually start writing, really functionally.
Mm-hmm.
At what point where you're like, okay, maybe I could try and implement, the monad. Like, was there a particular project that you had?
Oh yeah, it was. Yeah, no, it was for the book. I mean, I spent 11 solid. I mean, I probably spent easily well over 40 hours, a week for 11 months writing this book. Right, so I studied the history of it. Every piece of functional programming, I was like, I have to own it, right? Because these guys that write Go code, I mean, they're so smart, and if I'm wrong on any of my code, they're going to let me know it, and I'm going to be embarrassed, and I don't like to be embarrassed because, the engineers don't like to be embarrassed. We want to think that, we know everything, but there's no way to know everything, right? So, so I just, I did it for the book. I came up with stuff just like out of just sheer sweat and tears. I wrote the Y Combinator. You should seriously check that out. Somebody wrote a review of the book, and they said there's some scary stuff in there, and I think they were referring to the Y Combinator code because it's pretty scary. And here's another thing that's like incredibly fascinating and true. Okay, if you think about, like, if you're in biology, you remember back in, I don't know if they teach it, they probably teach it in high school, but back in the day, that was like I learned it in college about DNA and the double helix, right? How that works. It's got the two chains, right? And basically, cell growth works when you feed it information, okay? If you look at the structure of the double helix, and you look at the structure of the Y Combinator, in my book, I think I make it pretty clear that they are the same thing. As long as you feed it information, it will produce. It's sort of like a recursive program. You keep feeding it, it keeps going, and then when it's done, you get the result, right? But if you stop feeding it, cell growth stops. And, the structure of it, right? Just sort of like we studied the map, right? And it's like, you've got like 3 rows and, say 8 columns, and we want 3 rows and 4 columns, right? The structure, it's like this. It's the same. Well, actually, that's not a good argument. It's the same number of rows, but it's slightly different structure. But anyway, the Y Combinator and the double helix, I mean, it's like, maybe only God knows the answer, but the parallels are mind-blowing.
My follow-up question is actually, given that Go doesn't have tail call optimization, like, were there certain things that you ended up really having a hard time
Yes.
implementing?
Yeah. Well, I didn't have a hard time implementing it.
Because I know you could implement some of the tail call stuff directly using an iterative solution.
Yeah.
But,
Yeah.
Were there serious things that where you're like, oh, this could be better if I can actually...
Well, it's like all the patterns, like the functors and the monads and everything, when you write functional code, would benefit from having tail call optimization. I mean, it's just like, Haskell is, everything, you don't iterate, you call functions recursively. Right? And so if every time you call a function recursively, it's got to add that whole program onto the stack again, of course that's going to be inefficient. Okay, so but the sort of the point was, the monad, right? The monad, if you look at that structure, right, it's not a whole lot of logic to get that going. What really takes the time is when you lift, or in my case, I say you lower, right, to do your interactions with the world. That's what takes the time. So in that case, it's fully, it makes sense to actually use functional programming because it keeps it so clean. And basically, I have this function called next. You're at this state, and you go to the next state, and the next state, and the next state, and the next state, until maybe you get an error, and you still go next, but you go a lot faster if you have an error. But it just provides the structure. So in that case, functional programming makes a lot of sense. Now, if they would, that's why I kind of pushed and I was like, hey, please implement tail call optimization. And that's completely out of my hands. But the guys at what's his name, Chris, I forget. But he works at Uber, and he came up with Gleam. He's really got it going. You know, if you want to use Go and you want to use functional programming, you know, it's like if I do a next version of the book, I'm going to like eat up everything that's in that Gleam library, because you know he started out with Go and Lua, and then he found it wasn't performing enough. I mean, he went through a number of iterations. Just, you know, that's where I would look. That's where the good stuff is right now.
Thanks.
Yeah. Yes.
So you say you implemented the Y Combinator in Go, and I'm not familiar with Go at all. I don't know a lot of its features, and you mentioned it doesn't have tail call recursion.
Yeah.
And I don't know like how well it supports like call by name or call by value functions, but were you able to create a terminating Y Combinator function in Go, like one that didn't just recurse infinitely because of call by value or anything?
Yeah, check it out.
Cool.
Check it out. That's what started that huge thread that even Rob Pike, you know, responded to. And because it was like, they looked at it, it was like, hey, that actually works. It's pretty crazy. Yeah. And that was a part of the book where I was just like, please, God, let this work. Please let it work. Please let it work. I don't know if it'll work. I don't know if you've ever been in that phase of a program where you're like, I know I want to get over here. I don't know how to go over the chasm, right? But it just worked.
Right, yeah, I know, because I know a lot of languages, you can do Y Combinators even if they're really inefficient in memory because they don't have optimization.
Yeah.
But like if you don't have call by name or lazily evaluated functions, then they're just still going to recurse forever because they'll just keep trying to evaluate the Y Combinator without ever evaluating the values.
Yeah, no, that Y Combinator works.
Cool.
I mean, not efficient because it doesn't have tail call
works.
optimization, but it works. You know, just waiting for the become, you know, to be implemented.
Okay, so there's one concept I don't understand. Like, if you have like a maybe monad, and it can just, you know, pass an error all the way to the end. What would be the benefit of passing that error all the way to the end rather than just crashing the program?
It's, you know, it's just providing, you know, it's like a pattern, right? You know, it's like you know where the input is, you know where the output is, right? It's just like, you know, if you think it parallels, like I said, like the Unix terminal, right? You know, it's the same idea. You're going to pass data into the next function. If there's an error, it's going to come out. You know, there, like you could call, and I have an example of that where you've got, and you can think of, you know, you do a, I don't know, you do a find and you do an awk and you do a grep and you chain multiple functions. If any of them have an error, right, it's just going to go straight out to the.
Okay, so in other words, you want it to terminate at one specific place instead of wherever that error happened? Is that what you're talking about?
Let's talk after class. I'll show you. You know, I'll show you the code, but it's more of I guess how you say.
It's shortcuts, right? I mean, basically, we'll skip all the computation. We'll recognize that.
Yeah, it'll skip all the computation that's in the happy path when you hit the error, but it's just going to shoot right out the end.
Okay.
Yeah, I mean, it's not any slower. It's just, it's sort of like, maybe one way to think of it is, you know, you can write, like when you're writing imperative code, right? You can always return as your last statement, or you can have a return you know, up in your program somewhere, right? You know, you hit an error, you can just return, you know, from where the error is, or you can, you know, basically say, okay, well, this value is false to say you can have a value called ret, the ret variable. You can always return ret, right? Your ret starts off maybe true, and if you have an error anywhere along the way, you know, it's false. And then any of your little blocks knows, well, if it's false, then you're not going to execute that, and you're always going to know you're going to hit that last line. Okay. It's the same sort of idea. It just provides a pattern.
Okay.
Yeah.
Any other questions?
I've got an announcement on the
Yeah.
HTDC startup here. I'm the CEO and the founder. We've got a couple positions open for front-end developer, and so I figured someone may be interested. We prefer people that have full-time jobs and want to moonlight 5 to 10 hours. You can choose 5 or 10, and want to work on some cool shit. So, We're polyglot, so you can use whatever the hell you want. It's microservices, containers, and AI, so, and Docker. So if you're interested, I'm here.
Awesome. Thank you, Judd. Thank you, Ram. Thank you.